Hello everyone, and welcome to another exciting talk on protoplanetary disks. Today's talk will be given by me, Michael Hammer, a PhD student at the University of Arizona, currently looking for a postdoc, and will cover vortices and protoplanetary disks. This talk would not be possible without my collaborators Caitlin Crowder, Minkai Lin, Paula Pinilla, and of course the actual vortices and protoplanetary disks. But are there actually vortices and protoplanetary disks? Well, we think the answer to that is yes. In the past decade, ALMA has observed several crescent-shaped features in various protoplanetary disks. For a few of these, including HD 135344b, this one right here, we have observations of the same crescent at different wavelengths. If we look at the azimuthal extents of these crescents, the larger wavelength shows that the larger grains are more concentrated. Meanwhile, the smaller wavelength shows that the smaller grains that would be harder to trap at the center of a vortex are much more spread out. Now, that's the type of behavior we would expect to find in a vortex. But how did these vortices form to begin with? Well, one of the most favorable ideas is that they were generated by gap-opening planets. We can watch this happen by running hydrodynamic simulations of a gap-opening planet in a disk of gas. And most previous studies of this problem start with a gas distribution following the smooth radial density profile. They then add a Jupiter mass planet to the disk. And after running this simulation, they find that the planet will quickly open up a gap within about 100 orbits, which creates a sharp peak in the disk's radial density profile. If that peak is too steep, it will make the disk unstable and trigger the Rossby wave instability, which will eventually create a vortex. Now let's watch what that looks like. Now in this simulation, the planet grows to Jupiter mass in just 10 orbits. Soon after, the disk becomes unstable, forming several smaller vortices. Then, these vortices merge into one big vortex in less than 100 orbits. So now, the vortex has a width of about 120 degrees, and its maximum density is more than twice the initial density at the location of the planet. If we continue the video, we'll see that the vortex lasts about 7,500 orbits, which is more than 500,000 years if the planet is at 20 AU. If we compare the gas surface density to ALMA observations, we'll see they match up pretty well. But we shouldn't do that, because ALMA probes the dust, not the gas. If we compare the dust to the observations, you notice that the dust is much more concentrated than the gas. And in fact, it's so concentrated near the center that if you were to observe the disk from the simulation with a similar beam size, you'll see that the vortex no longer looks like the crescent on the left. Instead, it's just a small blob. Now, can we reconcile simulations of vortices with the observations taken by ALMA? Well, we weren't surprised when we saw those ALMA images, because we already knew that placing a fully grown Jupiter mass planet in a disk instantly isn't actually a good idea. Now let's take a look at what happens when we place the planet in the disk more slowly. For this simulation, we use the same parameters as the previous video, except that now we prescribe the planet to grow to full size over 1,000 orbits instead of just 10. Now in this case, when the planet reaches a fifth of a Jupiter mass, about 300 orbits, it makes the disk unstable and triggers a vortex. Though, this time the vortex is a lot weaker than before. It never reached as high of a density, and its width is about 240 degrees, which is twice as large in the other case. And even worse, the vortex only lasts about 1,500 orbits, which is 5 times less than when the planet was placed almost instantly in the disk. So there are two types of vortices. If the planet grows instantly, you form a compact vortex that's well described by the relatively new Gaussian model. If the planet grows slowly, you form an elongated vortex that's well described by the classic GNG model. Recently, Serval and Bard studied both types of vortices and found that the difference between the elongated and compact models wasn't so much the extent of the vortex, but really the minimum Rossby number in the vortex, which is just the amount of vorticity in the vortex. If the minimum was less than minus 0.15, then the vortex would be compact. And if it's more than minus 0.15, so if it's less negative, then the vortex would be elongated. Now it's relatively easy to see why a slowly growing planet produces a weaker vortex. When the planet grows instantly, it quickly creates a strong, compact vortex, and then that vortex smooths out the gap edge. But when the planet grows slowly, it forms a vortex long before it reaches its full mass. Since the planet is lower mass, the vortex that forms is initially a lot weaker and has an elongated Rossby number. As the planet continues to grow, it still tries to steepen the gap edge, but this time it has to compete with the vortex smoothing it out. As a result, the full mass planet can't strengthen the vortex or cause the Rossby number to drop as much as it does when the planet grows instantly. Now these elongated vortices look a lot more like the ALMA image that I showed before in the gas, but what about the dust? Now as it turns out, elongated vortices still trap dust, but not in the center of the vortex. Now just like with normal vortices, the increase in density at the edge of the vortex creates a pressure bump that, when combined with the rotating velocity field of the vortex, naturally traps dust. However, that is where the similarities end. If I add contours to both vortices, you'll see that the compact vortex has nice elliptical contours and a very smooth pressure bump, while the elongated vortex does not. As a result, once the vortex collects dust, that dust has no reason to spiral inward to the center like it does in a normal vortex. So what happens instead? Instead, the dust circulates around the vortex, as you can see here for 1 centimeter and 3 millimeter size grains. So this motion leaves the vortex nearly as elongated in the dust as it is in the gas. And furthermore, it also leaves the peak in the dust density off-center most of the time, creating a big distinction between compact and elongated vortices. Now with the dust circulating, do elongated vortices actually look elongated? The answer is yes, but not always. Now as the dust circulates through the middle of the vortex, it does typically appear elongated. But when the peak reaches the edges, it can also look compact. So with both outcomes possible, it's not straightforward to infer the extent of the gas vortex just from looking at the dust. Now going back to the beginning of the talk, we couldn't explain this ALMA image too well with a compact vortex, but an elongated vortex does a much better job. Now let's move on to what can kill the vortex. Now in the second movie I showed, the elongated vortex that forms dies out by eventually spreading into a ring. But why did that happen? Well, viscosity is one way to kill the vortex, but you need an alpha of at least 10 to the minus 4 for that to happen very quickly. And the movies that I've shown so far don't actually have that high of a viscosity. Instead, the elongated vortex in the beginning actually died because of shocks from the planet's spiral waves. But this doesn't always happen. Now if we increase the h over r to a very high 0.08, then the vortex hardly changes after it forms. Now it does decay, but you can see that it happens very slowly. And the vortex survives for thousands of orbits because the shocks from the planet's spiral waves are too weak to dissipate it. As a result, the vortex never spreads into a ring, and the vortex is still alive at the end of this movie. Now at h over r equals 0.06 though, we already saw at the beginning that shocks can kill the vortex in a little more than 1,000 orbits. But does that always happen? Now as it turns out, the answer is yes. But with lower mass planets, the vortex can actually reform. Now in this simulation, the planet only grows to about 0.2 Jupiter masses. Like the other cases, the initial vortex only lasts a little more than 1,000 orbits. But this time the vortex can reform. In fact, it happens at least 3 times, at about 2,600 orbits, at 3,150 orbits, and again at 3,660 orbits. And in total, the vortex survives more than 5,000 orbits and is still alive at the end of this movie, which gives it a way longer lifetime than the Jupiter mass case. So to summarize, vortices that are elongated can indicate the associated planet grew slowly. These vortices are often characterized by y-azimuthal extents and off-center peaks, but they can also look more compact. With h over r of 0.06 or less, low-mass planets actually generate longer-lived asymmetries than Jupiter-mass planets because the vortex can reform. And with an even higher h over r, the initial vortex might not die at all because the shocks from the planet that normally kill it are too weak to do so. And if you read our paper, you'll see that both of those effects are due to the planet's spiral waves. So yeah, that was the talk. If you have any questions, feel free to contact me. Thank you all for watching and have an excellent rest of your day.